This is the project presentation for Computer and Communication Networks, summer 2015. The group consists of Jake Anderson, Kevin Elliott, and myself, Marcio Oliveira. The topic we chose was data center routing protocols, and the specific paper is called SRP, a routing protocol for data center networks. The outline of a presentation, I'll just first show the topology we'll be using throughout the presentation and the one that we are using in our project, and just talk very briefly about data center routing. And then I'll talk about open shortest path first, which is the most used routing protocol for data centers. And Jake's going to talk about the Sequoia routing protocol, which is the protocol proposed by the authors of the paper, and how it's an improvement over OSPF. Kevin is going to talk a little bit about NS3, which is the simulator we are using to validate and compare both protocols. And then just a quick status of where we are in regards to the project. So data center network routing. So here's a typical topology of a data center network. In this case, and this is what we're using for the simulations, we have 512 top of rack switches and 2 levels of routers, the core and the border level. In a typical configuration like this, you can have up to 20,000 nodes in the network. And this is also what we call the single autonomous system. And what that means is that it's fully controlled by one entity. It could be a company or one person. They have full control of the entire network. So OSPF, or Open Shortest Path First, it's a routing protocol for data centers, what we call an interior routing protocol. So it's only inside a single autonomous system. It uses link state routing, so it knows about which links are up, which links are down, and how much is the cost of each link. And it's also, as I said before, the most widely used interior gateway protocol for enterprise networks. So OSPF is based on Dijistra's shortest path algorithm. Each node knows the cost of each link, which is broadcasted over the network, and each node has a table that is computed by finding the shortest path from source to all other nodes. So it's kind of similar to what we saw in class. And again, each node maintains its own, what we call a forwarding table or a routing table. So the complex for the protocol for any nodes in the network. So we need to check all nodes that we haven't checked yet, and it's usually O n square, but it can be implemented using Fibonacci heap, which reduces it to n log n. And the major problems with the OSPF is first high CPU utilization. You can see if you have 20,000 nodes in the network, and we are always computing the routing table because links go down and up, it can take a lot of CPU. Also, just looking at the table can be time consuming. And it has a very big problem when a link changes state, because it may take a long time for all the nodes to recompute the routing table, which can lead to packet loss if you have to route a packet and you haven't completely recomputed your routing table yet. It has a very high complex configuration, and it's easy to see. It's as the network grows, the memory grows considerably. The memory required to maintain all the information in the network. So the author's main point of OSPF. It's a good routing protocol, but given the new data center size, which are increasing by a very large factor, it's not suitable for those extremely large data center networks anymore. So now Jake's gonna talk about a little bit of SRP, how it works, and how it fixes all the issues we just talked about.
Hi, my name's Jake, and I'm going to be covering the Sequoia routing protocol. So in the paper we're doing, it talks a lot about the Sequoia routing protocol and points out the pros and cons of this versus OSPF routing protocol. And so this SRP versus OSPF, so they're both interior routing protocols. SRP is a routing protocol especially designed for data center networks. It's designed for the fat tree topology. It uses a grid versus link state database to keep track of which paths, which nodes are open and which the shortest path is. Grid uses an SRP controller, and I'll talk a little bit more about what the controller does. It's a newly developed interior gateway protocol, and it's used, like I said, mostly in data center networks. So the grid database is preset by the SRP controller. So instead of like the link state database where CPU utilization to run the algorithm every time takes up a lot of space and it can grow and shrink, SRP is preset. The link state advertisement is broadcast when changes in the table are detected, so it still uses the same advertisement as OSPF to update the tables, and on the bottom there's kind of a picture of one of the core databases that is used. So there's three types of grids essentially for each level of the network. So here it kind of shows you an example of that. So you have your controller over here, and this controller kind of divides your different subnets into different areas. There's a core grid, a Tor grid, and a border grid. And so as you go through and cover the different grids, you can see in the grid it tells you what links are up, which links are invalid, and which ones can be used, or backup links. If you look at the bottom right, it shows kind of what the backup links are. So one of the advantages of using grid in SRP is that it is a lightweight computation. It's operation oriented. It doesn't have like complex configurations. If you look at OSPF, it gets pretty complex as the network changes, and so that provides a benefit of fast transplant, switching in and out different network items. The routes are under control because of clear division of labor that's assigned by that SRP controller. As you can see there, it kind of divided up each table into its own section. Another advantage of grid is that it like I said, it presets the area instead of for the SRP routes versus a link state database, which grows or shrinks based on the network changing. It denies the routes that aren't preset. It maintains the relationships as any routing database does. It can monitor your subnets and check on the communication with its peers, and it modifies and updates its state as different routing states get changed and go down or other failures occur. So here's the SRP algorithm. It goes through essentially two for loops, pretty simple. So for each subnet in your table, you have a number of peers, and so when for each peer it goes through and says, okay, am I connected to this peer, and if I am, what's the state of that peer? Is it up, is it down? And updates accordingly in your table, as we saw before, kind of what the table looks like. So here's kind of an example of what happens. So when you get a link state advertisement, when something goes down in your network, the grid will go and check to see if the local grid contains the subnet. If it doesn't contain the subnet, it throws it out. If it does, it finds what subnet it is and then checks to see if that cell is invalid. If it's invalid, again, it throws it out because it's not connected. If it is valid, then it checks the message states to see if they're the same. If they're the same, it'll throw it out. If they're different, then it updates the message state. So whether it's up or down, it'll change the new message to up or down in your core database. And so you can kind of just see the bottom there, how it's an example of all the invalid routes and the ups and downs, and based on your connections in your network. So again, for complexity, you have m number of rows or subnets, n columns, so your total number of peers in the grid table. And so it's essentially the complexity of running 2 for loops, how much operation time it takes to run those 2 for loops within each other. And so that's why it's pretty simple to implement. So again, just kind of highlighting the differences. We have a grid versus linked state database. So grids in SRP, Sequoia Routing Protocol, versus linked state database, which was in OSPF. And the linked state database has to allocate a bunch of resources in order to grow and find the shortest path initially, and as well as when any changes in the network occur. Complexity of the algorithm. So on the left there is our Sequoia Routing Protocol algorithm. It's pretty simple, versus our linked state database protocol, which becomes complex, and when you're running your network and something happens, it has to execute those protocols again. And so overall, the SRP seems to respond better to changes in the data center network versus an OSPF, and that's the results we're trying to show in this paper that we've studied. Thanks.
Hi, my name is Kevin. I'm going to talk about our semester project, the network simulator that we've chosen, and our project milestones and progress. I'll start with our project goals. Our first goal was to explore packet routing protocols. This led to our choosing data center networks and their associated routing protocols as our paper. Our second goal was to learn a popular network simulation tool. And finally, we wanted to validate the author's claims in the paper we chose of improved performance using Sequoia Routing Protocol instead of Open Shortest Path First Protocol. 2 metrics are used to calculate this performance: route calculation delay and time to route convergence, both of these after a node failure or increased congestion in the network. We have 6 steps that we need to complete. First, we want to duplicate the simulation in our chosen paper. To do this, we need to learn the network simulator that we've chosen. We also have to add the 2 protocols, SRP and Open Shortest Path First protocols, to the simulator. We need to run the simulation. In order to stress the 2 protocols, we need to vary the network topology, simulate node failures, and change network congestion. This will help us validate the results presented by the authors of the paper. Our chosen network simulator is NS3. NS3 is written in C++ and Python, and it's extensible by adding models written in C++. To execute simulations, you write scripts in either C++ or Python. We'll actually write ours in C++. The build system for NS3 is called WAF. It's a Python-based system. It will build the simulator from source. It also is used to build models. When you add models, it builds the model and then adds those models to NS3, and then it builds C++ script files and runs the simulations. WAF is the command line interface into the NS3 simulator. In NS3, the primary object is a node, and whether it's a server computer, or it's a switch, or it's a router, or a client, all these are based on a generic node object. So you build these nodes up to act the way that to have the behavior of the device that you would like. So first you need to add an application. In our case, we'll be using a UDP application, and NS3 has something called the on-off application that turns the UDP stream on and off based on 2 random variables for the on time period and the off time period. that can simulate varying or random network traffic. These nodes are generic, so we have to add an internet protocol stack in order to understand IP. And then finally, to the node, we need to add a net device, which is similar to a network interface card, to interface with the channel to talk to other nodes. NS3 supports channels such as CSMA, point-to-point, and Wi-Fi. In our simulations, we'll be using the point-to-point protocol to talk with the other nodes in the network. Once you have the nodes built, we will work on the data center network topology. This slide shows the topology that both Marcio and Jake have described earlier. For the simulation, we will always be using 2 border routers. Over various iterations of the simulation, we'll vary the number of core switches from 2 to 4, and we'll also vary the top of rack switches from 4 to 1500. Each top of rack switch can support up to 48 servers. So when we initially run this simulation, we'll have 512 top of rack switches. So 48 times 512 is over 24,000 servers. And at 1500 top of rack switches, that will be 72,000 servers. NS3 provides helper classes to help build the nodes and the network topology so that you can build these complex and very large networks quickly. So why do we choose NS3? The simple reason is because NS3 was used by the authors of our chosen paper. That means that the SRP and OSPF models are already complete, and we also have examples of simulation. So our task was to take these 2 models and incorporate them into the NS3 simulator. WAF actually made this process fairly simple once we learned how to do this. We simply had to put the OSPF and SRP models in the correct directory in the NS3 directory structure, run the WAF command line interface, and it built the model and incorporated it into NS3 so that it could be used in our simulations. What this did for us was provided a faster time to run the simulation, and it also allowed us to focus on tweaking network parameters like node failures, introducing node failures, changing the network topology, and varying the traffic congestion, rather than fully implementation of the 2 routing protocols. We identified 8 milestones for this project that fit into 3 groups. First was preparation and research, learn the simulator, and finally demo and reports. Under preparation and research, we wanted to have the network simulator installed and tested and understand the code used by the authors. All 3 of us have the network simulator installed and tested, so this milestone is complete. We mostly understand the code used by the authors, but we still have some work on this milestone. Learn the simulator was essentially going through the NS3 tutorial. We broke this up into 3 milestones so that each one of the team members could work on a particular piece. So milestone number 3 was being able to configure the nodes with internet stacks. Milestone 4 was the network topology complete, understanding the configuration. This milestone actually allows us to vary the network topology and also introduce node failures. And then number 5, milestone 5, was applications running on the nodes. So all 3 of these milestones are complete now, as we've all 3 been through the NS3 tutorial. The final group of milestones are the demo and reports. This presentation will be complete, and the final 2 milestones, demo complete and project report complete, will be completed by the end of the semester, by the due date for these two items. So we appreciate you watching our presentation.